This is the panel on programming language security as extreme modularity. What we're going to do is, each of us is going to do a very short presentation. It's hopefully only going to take about the first half hour to get through all the presentations, so you understand each of our perspectives on this question. And then after the first half hour, for the remaining hour, we'll throw it open to free-form discussion, questions with the audience, arguments with each other, etc. Okay, so I'm going to start by sort of introducing my perspective on this topic. So on this slide is my summary of the history of computer security. Back at the beginning of time, i.e. in the late 60s, early 70s, there were two access control models. And pretty much in the entire history of computer security, you can see most security work is founded in one of these models or the other. One model that has come to be known as access control lists, or ACLs, is a model in which all security questions start with who is making the request, what identity is making the request, and then based on the identity that you find out, you then make an access control decision. And then the other one is object capabilities that starts off simply asking, the central question is this request authorized? And if it's authorized, then the request is allowed, and you don't care who is making it, and you don't even need a coherent theory of global identity in order to answer the question and to proceed by allowing the request. Okay. In the 1970s, as the computer industry was growing, it basically faced a fork in the road. Do we build out on one model or the other? And decades before we understood the nature of the problem we would have, the industry took the ACL fork in the road. Decades later, we had the rise of malware, and now we have the current situation. So this is the way I think of it. Early on, we made a speculative choice when we really didn't have enough information to understand the threat. Today, we're down here in this maze. We've now spent more than $1 trillion investing in searching the space to find a way to get to the goal of flexible, expressive, practical security. And we keep searching the space, and we don't seem to be making forward progress. The rest of the computer industry is making tremendous progress. This conference is an example of the tremendous progress that objects are making on expressiveness, flexibility, modularity, abstraction. There's all sorts of other areas of computer science making tremendous progress, but in security, if you look at the numbers, we're actually losing ground over time. So what's going on? Well, as we know from the computer science of search algorithms, if you make a speculative choice early and you spend a lot of effort searching the search space that descends from that speculative choice, you should at least consider the possibility that you're stuck in a cul-de-sac. And what you need to do is backtrack and take the other choice. But the problem is, we've already invested in building up this entire computer industry. We can't simply say, well, the whole thing was built on the wrong premises. Let's throw it all out and start over again. So we can't backtrack either. So we can't go forward, we can't go back. What can we do? Well, my answer is, what we need to do is we need to be clever. We need to find a tunnel somehow so that we can get from where we are onto where we would have been on the other path without losing most of the investment in the computer industry that we've built up. Now, fortunately, this would seem to be impossible except for this really fortunate coincidence, which is, as shown by this conference, object-oriented programming has been a tremendous success for purposes other than security down here. It's become much of the world of software has been built out on object-oriented programming, and the OCAP path, the object capability path, as you might guess from the name, has a logic to it very similar to the logic of object-oriented computation. So by building out from our object systems, not from our current security architectures, in order to get a different form of security, perhaps that's a way to explore the other path. Now, taking the other path is still no guarantee that you'll succeed. But we've spent more than $1 trillion failing on this side of the choice. We should at least try to explore the other side of the choice. Okay, now, this fortunate coincidence is actually not quite as random a fortunate coincidence as it might seem, because modularity and security are naturally aligned. What is modularity? It's designing components so that they hide as much detail as possible and they have few dependencies on each other. So avoiding needless dependencies between components. What is security? It's designing frameworks of interaction so that mutually suspicious entities can interact with each other without being needlessly vulnerable to each other. Vulnerability is a form of dependency. If I'm vulnerable to you, that means my continued correct operation is vulnerable to whether you continue to behave well. Anything that reduces vulnerability in a decent security architecture naturally increases modularity, and for those of us practicing object capabilities, that's what we've been finding in practice. I'm going to skip the rest of that. To get from objects, as we all know them, to object capabilities is a small step. Our object languages, many of them have memory safety and encapsulation. For example, in Java, pointers are unforgeable. You can only get a pointer if somebody gives it to you. So that's memory safety. And encapsulation means if you and I are objects, I have your public interface, I can only invoke, if I have a reference to you, I can only invoke your public interface. I can't reach through that to get at your private state. That's encapsulation. To that, we only need to add 2 further restrictions to get to object capabilities. We need to restrict our languages, or our platforms, so that an object can only affect the world outside of itself according to the references that it holds to other objects, by making use of the reference it holds to other objects, and that an object is given no powerful references by default. With these 3 rules taken together, objects are born naturally sandboxed. They come into existence with no ability to cause effects outside themselves other than those explicitly granted by the environment instantiating the object. We get the following 4 benefits from these 3 restrictions taken together. The access graph from the access control literature, also known as the access matrix, becomes identical to the reference graph from the programming language literature. We have a nice graph connectivity property. We call only connectivity begets connectivity. 2 disjoint subgraphs can never become connected. 2 almost disjoint subgraphs, this is the interesting part, 2 almost disjoint subgraphs can only interact or become further connected according to the decisions of the objects that have a foot in both. So those are the strategic places to place the objects whose behavior expresses your security policy. And, I'm going to skip least authority, this brings, most important is that it brings the power of object-oriented expressiveness brings that power to bear on what is otherwise the difficult problem of expressing security patterns. What we find is that many security problems that are thought hard, when done in this way, bringing object design insights to it, can be expressed with simple, clear, elegant pieces of code. So I just want to close with these 2 columns. The elements, I'm not going to go through the rows. The elements on the left column are the recognized practices of good object programming done right, good software engineering with objects. The elements on the right are those that object capability practitioners have found to be the elements of good object capability design, and all the elements of the right are a natural extension of the corresponding elements on the left. And now I'll turn it over to the next speaker. And Marc Steigler. I'm sorry, I didn't introduce people. Marc Steigler, Dean Tribble, David Wagner, Jonathan Shapiro. Marc Steigler is at HP Labs. He did the breakthrough system on secure user interfaces, as well as collaborating on use and design of object capability languages. Dean designed an early distributed object capability language named Joule that has inspired several decades, more than a decade now of my own work. David Wagner is a professor at Berkeley that taught me how hard security actually is, even with a good paradigm, by attacking my system and showing how it had holes all over the place. And I've become a much better practitioner because what's in my head from now on is, how would this withstand an attack from David Wagner?
And the answer is it would not.
Yeah. And Jonathan Shapiro, he was my thesis advisor. He's the one who's carried forward, done the most to carry forward the investigation of the capability operating systems. And he's also more recently done some great work on languages in which you can build systems programs that you hopefully can prove correct. Okay, those are the introductions.
Okay. So as Markham was saying, I'm Marc Steigler. I'm with HP Labs. And this is a really short intro to how modularity gives you security properties. And this is the 6-minute version of the talk I did at Google. You can see on YouTube, The Lazy Programmer's Guide to Security. But in any event, we're going to start out by looking at some JavaScript here. On the left-hand side, you'll see a piece of code that is unmodular. Okay. In this piece of code, we've got a function that creates a table with 2 entries. There's a value and there's a password. And then it calls upon this other function that is going to use the first entry for some purpose. And in order to give him that first entry to use, what he does is he sends him both the table and the key, the index into that table, so that he can reach the value that he's supposed to use. And up here, he prints that value. But while he's there, since we gave him the table, he also prints out the password, okay, from that table. Now, this, of course, is quite unmodular. I'm sure that this is a room full of object-oriented practitioners, and no one would ever, in this room, write a piece of code that this was non-modular. It is obvious to every reasonable OO practitioner that instead of sending both the index and the table to this guy who's supposed to use that one element, you just simply send the one element. And so down here, when we call the function, we simply call it with the one element that we're supposed to be using, not the combination of the index and the table. So this is normal modularity. Okay, just about any of us would do this all the time. So far, so good. But now suppose we're going to have a function that was going to edit one entry in that table. And so for this, it is much more alluring to send in the index and the table because there's a lot more code involved to give the guy just the authority to edit the one entry. But suppose that you are handing you are handing this value to a function that was being written by a third party, and it was a third party that you didn't know real well, and you didn't think he was malicious, but he might have an accident, and so you're a little bit worried about this guy. So what you might do in that case is instead of sending in the index and the table, you would send him a function that was a setter that would do nothing except set the specific value that he was supposed to be editing. And you can see down here that what we do then is we send this function to the editor, and he just simply handles that. So that's actually only 2 extra lines of code, but it's enough overhead that I have to confess that on a normal day I might, if I were sending the value to a function that I was writing myself, I'd probably do the unmodular version. So this is more modular. This is a little bit extreme. We're doing it because we're going to hand it to somebody that we don't entirely trust to be reliable. But now suppose that the editing function is going to be written by the boss's son, And the boss is really determined that his son is going to be a programmer, but the boss's son actually wants to be a surfer. Okay? And I'm pretty suspicious that he is going to go out of his way to make the software break to frustrate his father so that he can get back to the beach. Okay, in that case, okay, now I'm going to be a little bit paranoid. And what I'm going to do is not only am I going to send him a function that's a setter, but I'm going to send him, but this setter is going to be manufactured using another function that makes a one-time only editor function. Okay, so that's this function. And down here, when we invoke the editor, we give him this edit once function, and that's all he can do. And now he cannot succeed in setting the value more than one time. Now, somewhere between the beginning and the end here, we moved from doing just simple, normal modularity that everyone would do all the time to a form of modularity that was so extreme that it was protecting us from someone who might actually be malicious. Somewhere in that transition, we went from simple modularity to modularity as security. And so that's all good. The only bad problem, of course, is that languages like JavaScript only present the illusion of modularity. They don't supply real modularity, and that is why you have to use a language, either a verifier or a rewriter or a language from scratch that supports true full-fledged modularity. If you are using if you're a JavaScript user, you could use Caja or AdSafe. If you're using Java, you could use Joe. And there have been object capability versions of various other languages built as well. So anyway, so that's a brief introduction to modularity as extreme security.
You've got it all backwards.
Oh, no.
Well, so you're talking about modularity to get security, which is a lot of what object programming can bring to us. But what I'm going to talk about is the opposite direction. So I'm currently at Microsoft, but my prior company started early days of the internet, a company called Agorix, and we built, a few of these people worked there at one time or another, including me. And we built high-end electronic commerce and business-to-business software, so banking software for Schwab, software for the bank, software for Sun, and so forth. And these had security as an important requirement. And the thing about security that a lot of people miss is you can screw it up at any level, right? You know, at the OS, if you messed it up there, it's just irrecoverable and you're out of luck. Right? If you then go to a language and that gives it away, well, you'd better not run anything else on that same language platform except the one thing that you trust, because that gave away the store. You know, and so each level up, you can add more libraries that, you know, I've got a web interface and it's got a login interface and it sends the password in the clear and I just gave it away. Right? And so what was important to us was to have tenets of design that gave us security at every level so that we didn't give it away at one of those levels. Okay, so how does design kind of work? You've got some bunch of functionality for a bunch of requirements that you have to address. Yeah, there's a lot more to design, but the part I want to focus on is of these things, I'm going to partition them up into objects. So I'm making a banking application, and that means I've got to, be able to on a particular account, withdraw funds and deposit funds and go to the vault and see how much money is there and, clear things to the Fed and all these sorts of stuff. And when you look at that, I've got, well, gee, do I want deposit and withdraw on the same object? Do I want check the vault balance on the same object? Where do I put these functions and how do I divide up my design? So usually what happens is, of course, you take a cut at it as you evolve this system, and you put a few boundaries in the wrong place. You separated the wrong things. I've only been 1 minute. Yeah. And sometimes you put boundaries where you didn't need them, so you start tripping over them. And as you evolve these boundaries, as you go forward, you evolve your design. And the problem is that every step of evolution introduces the later you evolve it, the more expensive it is. You've written more tests, you've written more documents, you've explained it to more people, you've got more code that depends on it, and so evolving your design is more challenging. And as every time you evolve the design, you might leave something behind. So you've got security holes, or you've got bugs that you introduce. And of course, in this context, those would be security bugs and security holes. So we had a set of design rules based out of Kikos, based on capability, based on capabilities, for how we did object design and how we did overall system design. So here's the first 3 rules, and these are the big ones, and there's a few others that I'll eventually reconstruct for us. But, so represent distinct authorities, or represent distinctions in authorities with distinct objects. So the ability to check the vault is going to be done by a different person than the ability to withdraw money from a particular account. So those must be, according to this principle, separate objects. So now I have a very clear-cut distinction in my design that I may have more objects than that, but that distinction has to be there. Another is combine implied. So the second one is combine implied authorities. If I can withdraw all the money from an account, I can probably find out how much is in there, because I can just pull it all out and count it. So there's not a lot of value in that context of separating those into separate objects, since given the ability to withdraw an account, I can count the money. Now, maybe I would want to give someone the authority to check the balance of the account without being able to either deposit or withdraw money from it, in which case that might want to be a separate object, but there's no reason to have the how much money is there, the account balance query, not be on the object that lets me withdraw. And then the final one that I'm going to talk about here is the avoid increasing authority via subtyping. And this is the one that is unusual for object-oriented programmers. The other two are actually quite natural. Rather than looking at the account case here, I'll take a read-write stream. If I had an operation that returned a read stream on my precious data, so I was going to give you the authority to read it, it would be unfortunate if I, who had the authority to read and write it, took my read-write stream to let me write my important precious data that I just spent a bunch of money to collect. I'm sharing it with you, and you get this thing which is a read stream. You go, gee, I wonder. Let me cast it down to a write stream and try and scribble on it. Oh, look, he just erased all my data. And so there is this. So that risk showed up in a few different commercial products where where a subclass, where you'd have a read stream and a read-write stream as a subclass, and that added authority and that introduced bugs. And so we end up in capability-based design, instead of there being inheritance, those are two sibling classes, and maybe you can get one from the other, but you can't accidentally in the type system reveal a stronger authority than you intended. And my last slide. So where did this lead us? We built a lot of large-scale systems, and in designing for security, because that was important, we tripped over better designs. We ended up with systems that were better designed than we had expected, both under versioning and under maintenance. And the question is, why did that happen? The first is exactly the point of this whole thing. Security is really preserving modularity, preserving availability while under attack, which is simply more challenging than preserving it while, under maintenance. Right? The reason why we ended up with better designs, though, is security requirements are visible early, and security requirements are visible to the domain experts. So that means when you go in to do requirements analysis, when you go in to understand the problem, those lines show up early. That means less evolution of the design. That means a more stable design over time and over versions. So that's it. So that's why security is important for modularity.
All right. Hi, everyone. I'm Dave Wagner from Berkeley. And I want to get you thinking about how to build code that facilitates and supports security code review. That makes it easier for you to review the code and gain confidence it's secure. I spent a lot of time doing security code review, and boy, it's incredibly painful and tedious stuff. Why is that? One of the reasons is because the way we build code today often has the property that a bug anywhere in the code can compromise the security of the whole thing. So that means the whole application is security relevant. You have to review it all. And it's worse than that because any interaction of a pair or combination of features from the application could potentially have security implications that could ruin security for the whole thing. that makes code review hard, especially given our limitations as humans. As humans, it's very hard to keep a lot of code in your mind at one time. It's kind of like we're looking at the code when you're doing security code review. You're looking at the code through a straw. You get to see about a screenful or a couple of screenfills. And I don't know about you, but I just can't keep that much code in my head at one time. And that makes it really hard to get a global view of the security of the application. So imagine if we went around living life with our vision being seeing the world through a straw. Right? We'd miss an awful lot of stuff. We could go to the museum and we might see a painting and it would look like this, and you might see this. And then you kind of shift your perspective and look over a little to the right, and you see this, and you see this. And you start to get a look around, and you're seeing here it's looking like a pretty, seascape with some sky. But you've missed something very important because this whole thing's about to come crashing to the ground. And security code review is often a lot like that. So the point I'm trying to make is, if we want to help people do security code review, if we want to design languages that facilitate that, then they need to take into account human limitations. The fact that we can only look at code through a straw. And that means we really need languages that make it easier to spot bugs, that we need to facilitate construction of code where bugs are locally obvious. And this is one of the requirements that then drives the reason why modularity is so valuable for code review. And the second thing I would say that would really be nice, would be great if our languages and the way we build code helped us identify which portions of the code were security relevant, or were relevant to a particular security property we had in mind, so we didn't have to inspect the whole darn thing. Okay? So that's the perspective I come from, frustration with the challenges of code review. And one of the things that got me excited about looking at the object capabilities approach is because object capabilities, it seems to me, have the potential to address some of these needs. In particular, what they give you as a code reviewer, when you're looking at code, is they give you security theorems for free. And oh boy, this is so nice. First of all, they help you, maybe most importantly, as you're reviewing code, they help you identify which parts of the code might be relevant to the security property you care about. So let's suppose I'm reviewing an email client to determine whether it can start spamming my internal contact list, or sending other network connections to go attack, by a worm, some other machines on my network if it becomes compromised. Well, I might have some code here that looks like this. If I look at this piece of code in an object capability language, if this is written in an object capability language, then by inspecting this code, it's possible to identify what capabilities that renderer object receives. And in an object capability language, that tells you what the renderer can do, what side effects it can cause, how it can affect the outside world. In particular, in this case, we're giving it only access to a window, and so from that we can conclude automatically, without having to look at the code or the implementation of the renderer, we can tell immediately that it can't trash my hard drive and it can't send anything over the network. Okay? Even if there's a million lines of code behind that renderer that's able to render, HTML and do all sorts of magical stuff, I don't have to look at it. Okay. So that's where my enthusiasm comes from. If you're interested in more reading, I'll point you to 2 papers I happen to like. I'm biased. And what I want to finally leave you with is I want to get you thinking about how language design and how system architecture can help facilitate security code review to make it easier to review code and get some increased confidence in its security. Thank you.
So when Mark asked me to come join the panel, it was sort of strange because I think of myself as an OS guy. There are lots of people who want to think of me as a security guy or a languages guy, but in fact, wow, what just happened? Maybe we'll try that. Huh, maybe not. Okay.
Is it something that I could project from my laptop or somebody?
Just give me one more try and then I'm just going to give up. This is great. I tested this earlier, and I can even tell you what's going on. This projector doesn't do EDID, and so the iPad dongle won't talk to it. All right, so my background here is I'm a reluctant PL person. I've spent the last several years working on a programming language called Bitsy, which actually is not an OCAP language. And the main purpose of this language was to let us build a capability OS with higher confidence. So I'm kind of looking at this more from an OS perspective than a PL perspective. I think it's fair to say that the transition in the L4 system to capabilities is something that was inspired by the Arrow system and the Coyote system. And Mark, I have heartbreaking news for you. That means that we have won. Because there are now both more pure capability-based operating systems shipped and more in daily use than any other kind of operating system. If you have one of these, you're running a capability system. Okay? There are more capability systems out there than there are copies of Windows.
What is that?
It's a cell phone. All of the ARM-based smartphones now to first order are running a capability-based OS at the bottom. So I'm now working on a stealth mode audio startup, which has nothing to do with this conference at all. And for a brief window of time, I was involved in the Modularity project at Microsoft, which is a language-based operating system. And I'm mostly going to let Dean address that if he chooses to. But I took my task as a panel member to look at language issues in operating systems. And when the panel was originally described to me, it was a language-based security panel. So what does that mean? That's a term that's changed. When that term was introduced, it meant let's take the things that have traditionally been done by operating systems and replace them with language-based technologies, because maybe we don't need that operating system stuff, and we have a much better handle on semantics in the programming language world. That's an idea that's gone in and out of currency. It recently generated a lot of Singularity, I think, put a lot of excitement back on it. And of course, when Microsoft introduced the Modularity project following on that, there was a kind of a revitalization of that excitement. I think the thing to say is that language-based so security is entirely about encapsulation. You've heard that amply. Language-based encapsulation as a vehicle for security, whether that's appropriate depends on what granularity of problem you're looking at. So as a solution for intra-application isolation, great. It does not work as a replacement for an operating system. And the reason it does not work is that it introduces 100 times the complexity in the trusted computing base, because now I have to trust a very large language runtime or I have to give up efficiency. It multiplies the thermal load in the memory system by a factor of 3. Google will never adopt Go for the back end. And it's not because they don't want to, it's because they can't afford the heat. Okay? To run garbage collected code as efficiently as C++ or C, you need 3 times the memory. There are 2 people in the world who know how to build garbage collectors that can make that statement true. The rest of you need 10 times the memory. And there's a significant performance loss, okay, because there are overheads in safe languages. So more recently, though, language-based security has kind of been generalized as a term, and it's popping up, I think, most visibly in the browser world, where I think it's introduced new capabilities with huge promise. I think it's sort of wonderfully promising there. One of the problems we have is that existing languages are actually really ill-suited to this, right? Because they weren't designed to express issues about permission, and at some level, they weren't designed to express issues about encapsulation in the presence of hostility. So people have the idea type and memory safety somehow is a universal panacea, and if we maybe extend it a little bit, maybe we augment it with a few tricks in the runtime, we'll have all this kind of stuff done. Well, that doesn't seem to be the case. First, type and memory safety leaves a lot of other resources out that we care about. But second, there are failures of inclusion. When we say type and memory safety, we often tacitly mean garbage collection. And when I'm doing resource management with garbage collection or reference counting, one of the things that happens is I share an object with Dean, and Dean doesn't let go. And I'm paying for it. Okay? And that's a systemic failure source, which is actually a real problem. And so one of the stories about language-based operating systems is, gosh, I can avoid a bunch of copying issues by sharing objects. Unfortunately, that turns out not to be true. And it's not true for 2 reasons. One, because Dean's not cooperative. Sorry, Dean. But the other, and this is a more subtle point, if I have multiple applications running in a system, we don't yet have a universal garbage collector. So different applications, in order to perform well, may need different GC technologies. That pushes them into different object structures. And now we're talking about two runtimes that don't agree about the object structure trying to share an object reference. And that doesn't work out so well. So pretty soon you say, well, okay, I won't do that. And now you pay all the cost of marshalling, which was the major source of potential performance gain, and all the cost of carrying a large, complicated runtime. Okay. So the last point I want to make is that when we talk about things being secure up to resource denial issues, like Dean holding onto my object pointer, Dean's going to pick on me later, so it's all, all fair in love and war.
We're all going to pick on you in a minute.
Excellent. That seems that seems about fair. Secure up to resource denial is insecure. It's just that simple. Okay, unless you've got an answer to the ability of one domain to deny resources to another, or equally to deny access to resources. So if you're holding a resource and I'm accounted for it, that means I can't allocate some other resource I need. Right? That's not a secure system. It's not even a robust system. Another issue in sharing is that cross-domain trust, if I can abuse a term, is generally asymmetric. Right? The client has to trust the service that it relies on. The service must not trust the client, because presumably there's another client, and these two clients I don't know what their contract is if I'm the service. I've already hit that. And I've already hit that. So we've heard from Dean the, sort of the security is virginity model, right? Don't give it away. And I was really, really trying to stay away from these metaphors in this talk. So I want to offer you, the security is social disease model, in the spirit of what today, I guess. There are consequences to sharing. And with that, I think we maybe should get on with the panel, and I should shut up. But thanks for coming.
You're sharing too much.
Too much.
It's Dave Unger here, of course. I'm always here when I'm here. It's great that I don't need to get you fighting among yourselves. I think we'll do that. But a quick comment and then the question. The comment is, as far as looking at the world through a straw, my understanding is we do that because of foveation. And the illusion that you can see more than a little piece at a time is a constructed thing by your brain. And the blind spot illusion kind of shows you how real that feels to you when it's not. So, bad analogy to use for people who think about the human visual system at that level. And maybe when we think about analyzing things, there's a lesson there. But that's not my main question. You guys can address that. The Ken Thompson Turing Award lecture.
Oh, yes.
Where, do you guys want to explain it? Do you want me to explain it?
If you'd like to, I'm happy to.
So, the way I understand the story, and please correct me, Rand Corporation said we've developed a provably secure Unix. Ken Thompson made some bet he could break it. They let him visit them. He sat in front of a teletype or terminal, waggled his fingers, and in a minute he was in his super user and won the bet. And the way he did this was, they started with the C compiler source. Well, the C compiler is distributed by Bell Labs, and then compiled their compiler through the C compiler and compiled their OS code through their C compiler. And their C compiler contained code that when Ken logged in with the secret password, would let him in as super user when it was compiling the login program by recognizing lines in the login program. And it contained code that when the compiler was compiled through itself to basically insert the algorithm even though it wasn't in the source code of the compiler. So language-based security is bunk, right? Because look at what Ken did.
It's a good point to address, but before we do, this is a story that has grown in the Apocrypha over the years. Ken is on record that compiler was never deployed.
Never written?
Never deployed.
Oh. Okay.
Never deployed outside AT&T or never widely deployed within AT&T?
Even within AT&T.
Oh, okay.
I didn't know that.
But it's still a valid litmus test question and a question to explore. So let's do so.
Okay. I'm the moderator. You guys.
Well, you can give away security at any level. One was trusting Ken. Oh, no.
Said the guy who's holding my objects.
That's right. So that issue broke into an OS, right? So this is a general security question. It has nothing to do with language versus OS security. It has to do with using a untrustworthy tool set for a security purpose, right? And he was in a privileged position with respect to the tool set that they were going to use, right? So there is certainly in any system you're building, and indeed one of the points of BITSI, one of the points of several efforts around what's the pedigree of the tool set I'm using to produce this secure artifact. It's that pedigree, and it doesn't matter whether it was the language tool set or I take a kernel built some other way and I'm deploying it and my deployment tool squirrels in some additional rootkit, and now that machine goes out pwned from the get-go. It's not. That's about general security architecture and practices independent of language.
So if I may follow up, given that we can have bugs in compilers, isn't language-based security bunk?
No.
Again, the more general point is, given that there may be bugs in compilers, any security, whether it's borne by a language or an operating system, is bunk. So
it's only as good as your tool set.
Yes, it's only as good as your tool set.
Yeah,
which is why we have Jonathan developing BITSI.
Well, except that I've stopped. So I've heard it alleged that software verification applied to the C compiler actually could have prevented that if one imagines it had been spec'd correctly. And so let's stipulate for a moment that that's true. I think what I want to point out is that security isn't black and white. It's a matter of raising costs. A lot of us in this community love the idea of software verification. It generates lots and lots of research dollars and papers. Imagine we had it. Right? What portion, if you, in fact, let's talk for a second about what's going on in Australia with OKL4, where they've done an enormous amount of very impressive work on this. I think there's some reason to doubt that they've correctly stated the properties, but they can fix that. If you put together a pie chart and said what portion of the critical software in the system has been successfully verified, you couldn't find the wedge. And so I would say it's not a matter of all or nothing. It's a matter of raising the bar. And the Ken story is entertaining, but Ken isn't the most important threat model.
Okay.
The other addition is, partly there's a defense in depth thing where the bigger problem there is the architecture of that system was such that one vulnerability and you own the entire thing, right? In more secure systems, one vulnerability and you own the one thing you broke, and the rest of the things are fine.
That's right.
You're saying the presence of the root account was actually the fundamental error.
Yeah, because some administrator that actually knew the root password had the same universal authority on that box that he shouldn't have had.
I'll be stunned to learn that someone has applied verification to a real optimizing compiler or a real, say, dynamically optimizing virtual machine. If it's true, I will be stunned.
I'm somewhere between you guys and Dave on this. I think I'm somewhere between these guys and Dave on this question. The fundamental point that I agree with is the one that Jonathan made, that it's about raising the bar. It's not about absolutes. But the form of vulnerability that Ken's attack is an example of is supply chain vulnerability. And supply chain vulnerability in general as a vulnerability, even if you could successfully reduce the worry you had about Ken's specific attack, which I think you can, nevertheless, supply chain vulnerability in general is a terrible weak link. How do you know that the chip manufacturer didn't put a trapdoor in the chip design? How do you know that there's not a keystroke logger in your PC? I mean, they're just all security reasoning starts by saying, assume at T0 you have a machine, or whatever your platform is for security reasoning. You assume a platform and you say, assume at T0 that platform is not corrupt. The only basis for introducing that assumption is that if you didn't introduce the assumption, you would not be able to take any further steps in the reasoning.
The chip issue is very immediate. The American defense community right now is terrified about the fact that all of our chips are manufactured abroad, but they're even more terrified about the fact that as a country, the United States no longer has the capability to get back into the fabrication business. And I don't want to get into a cross-country competition issue, but the supply chain issue is very real.
The other thing I would point out, one last thing to say, no, this is backwards, is even if the language gave me no security properties, having designed for security got me those other advantages of modularity and maintainability of my code that have nothing to do with security. And so I'm perfectly happy having the security design constraints in the same way that I have a type checker to help me do better design for other purposes, for performance and so forth. I didn't hear you.
Next question.
Chen Ding, University of Rochester. This panel is extremely interesting. But I need to say security is not my expertise. In fact, I should be going to a paper upstairs as my day job. But I just resonate with what David Wagner said, and then I want to offer an observation, and the analogy may or may not apply. So just reading from my notes, he said languages must respect human limitations, support local reasoning, help us identify relevant code, and bugs should be locally obvious. And this can be said without change about program parallelization or parallel programming support. Mm-hmm. And people have been working on that for a long time, including my work. And modularity doesn't, so it's not that it haven't been tried, but I don't think people would think that modularity will be the key to solve this problem. The effective solutions in recent past has been some unifying, it's like a garbage collector, some unifying solution to solve at fundamental level. For parallelization, will be dependence, for example. But that's just since you're talking about modularity, it just struck me that from the angle of parallel computing, that it seems a different experience we have.
One of the things, I'm going to address, there's a connection between concurrency and security. I'll just mention the subtitle of the thesis that I did for SHAP, for Jonathan, is towards a unified approach to access control and concurrency control. A lot of concurrency paradigms assume that all of the interacting threads are mutually cooperative, and they sort of depend on the continued sanity of the concurrency system, if it's working at all, depends on everybody playing by the rules. Those of us who've dealt with both concurrency in the context of a system populated by mutually suspicious entities, had to find a different way to approach the concurrency problem that was robust against hostile clients operating within that same concurrency context. I'll just leave that one at that.
Okay. I'd like to point out that there is a particularly delicious article you can find on the web. It's entitled Dinner with Satan. Okay. And this is the problem that Doug Crockford posited a few years ago, in which you take the basic dining philosopher's concurrency problem, and then you say, oh, and I forgot to mention that one of the diners is Satan, and his goal is to starve the philosophers to death. Okay. And so this is a problem for which concurrency and security come together in a most ferocious way. It's a delightful and entertaining article. And he solves it using an object capability language, a very early version of E.
Yeah. And it's not just an object capability language. It's an object capability language whose concurrency model is communicating event loops. And it's these security concerns was one of the major issues that drove us to that concurrency paradigm.
So I guess I'll throw in, since the original question was, is modularity going to be effective for security? And there was some skepticism about whether it would. I guess I would just make the point that today modularity is one of the key tools we typically use for security. We just don't call it that, and we do it at the system level. We have isolation at the level of machines or VM instances or entire networks, so that if my favorite website has a security vulnerability, sure, all the information that website is responsible for holding may be breached, but it's not that the entire internet becomes insecure. So we do rely on modularity right now drawing these kind of security boundaries as a crucial security tool. It's just that the way we do it right now is very coarse-grained. For me, I see one of the appealing aspects about language-based security is the potential to do this on a more fine-grained basis.
So part of that, maybe it's useful to ask, so why is encapsulation helpful? Just at a very high level. And if you look at how programming language-based systems that have tried to have a security story have been constructed, you always discover that down at the bottom there are a few bits of code that do some operation that you in general are not allowed to do. And we might as well call that privileged code, because it is. What encapsulation gives us is two things, right? First, it gives us the ability to write code that chooses not to disclose. And that code could be privileged or it could not be privileged. Doesn't matter. But the ability not to disclose is something that we all kind of at a personal level take for granted, but in a software level it's not at all something you can take for granted. The second thing it gives us is then the ability to control propagation of, well, the term we use is propagation of authority, but it's really what it means to hold a reference is the ability to invoke the operations that some object chooses to publish. And what it means to be a reference in this kind of system is that by choosing not to pass references along, I can hold the ability to invoke something that I can deny you unless you can get it from some other channel. Right? And from that, you either can or cannot build a system structure that actually works. But if you don't have that, I guarantee you can't build a system structure that might work.
There's
so encapsulation is important both for as kind of the step zero of putting a barrier around the privileged code that you can then talk about doing containment on, and also about writing code that doesn't have to disclose. So
one of the an analogy between security and parallelism things that I can choose not to disclose is much of security, a lot of times you look at functional requirements and what does this thing need to do? Much of security is what does this thing need to have be impossible? What does this thing need to not be able to do? What is it that I can do that I know you can't? And looking at object systems like sort of the baby JavaScript, the stuff pre the protection things that people have added, where here's this thing that has fields and it has methods, and I can reach in and look at and from outside and mess with anything. But most people don't program that way. They programmed as if this record that this thing made only operated on itself, and I'm just going to call these functions on it. So they programmed as if it was encapsulated, but because they weren't guaranteed of that, you can't look at the code and know that random weird permutations of this thing don't happen because some other program that I didn't look at the same time didn't reach in and mess with it. And so that thing about being able to choose not to disclose, or what anti-guarantees am I provided? What guarantees am I provided of things that can happen also shows up in parallelism, right? Which is, synchronization is a lot about knowing that guy can't block me from his thread, or knowing that I can proceed independent of what all the other threads in the system are. And at the next level up of security, where it's, availability under attack, that turns out to also, those kinds of concurrency issues turn out to also be security issues, right? If that guy can run and starve me, even though he hasn't touched any of my data or interacted with me at all, he's talked to the scheduler and arranged for me to be unable to deliver service to my customers, that's a denial of service attack.
Hi, John Brown at Walt Disney World. I'm also not very much of a big security expert. But I do agree with kind of a lot of the things saying here. I do agree that modularity and security do have common goals. but I also see along the lines is, what I'm kind of looking for is, you could have the best lock in the world, but if you hand out copies of your keys and put one under the mat, it's the practices that and a lot of the social tricks that happen now that seem to cause security issues. And I had just kind of recently gone through a whole book study for our Java developers over effective Java. And the first one I read through that book, it sounded like it was a bunch of levels of security components on how, because once you break encapsulation, you introduce the risk of, the security risk. Once you introduce mutable objects, once you introduce serialization. So the whole idea of, we get a language that has the security, features built in, I think it's a great idea. But I think what, I guess it's similar to the concurrency. If we're building it for the purpose of helping a developer develop more secure applications and think of that during their design process, I think that's probably the more important aspect that I've seen of it, because when I was looking at it, I just looked at the many ways in that effective Java book that, security could be broken. And so, and I assume that, Java is a fairly modular language.
Yeah, so amen. I mean, one of the things you said that really resonates with me is that we're building a system that has to work with a human in the loop. And who's the human? It's the developers. And their practices and what works for them is essential. So I'll just plug a little bit of recent research that my group is beginning, which I'm really excited about, which is looking at, there's been an enormous amount of technology proposed for security systems. Static analysis tools, better languages, maybe supposedly some languages are better for security, practices and procedures, maybe it's training, maybe it's how you write your code. We're starting to look at which of these work for developers by trying to run rigorous experiments with real developers and then measuring how secure the resulting system is. So, for instance, here's a few questions. I'll just give you the teaser. Here's a few questions that people might like to argue about. For instance, when you're building a web application, what do you think? Is Java better for security than PHP? Or here's another one. Statically typed languages, better for security than dynamically typed languages, or worse? If you're interested in that, read our paper at Web Apps this year, or come talk to me and I'd be delighted to tell you about this research.
I'm an architect, so I would say it depends. That's also the answer lawyers give. So another response I want to make to that is, that goes back to the you can give away security at any level. Java, at the core, the core, I've got an object, it's got encapsulated objects, unlike, Ruby or JavaScript or some of these other things. But there is this layer where, there's some code that gets to say unsafe, or gets to say, I get to do weird security manager stuff and I can poke inside of you and serialize you. The current version of Java might be secure, but one of the important things is there's the language and there's the libraries. And as the libraries grow, if those are privileged libraries, they may add, backdoors or holes into stuff that used to be secure. That doesn't compromise the language, but it does compromise a particular runtime or a particular environment. And so those are all, important design issues. But it still remains that from a design point of view, if you went in and discovered that hole, right, great, maybe I can fix that, maybe I can fix that library. That's very different than, oh crap, I have to re-engineer the entire thing because I didn't think about security at all throughout it. So I have no isolation at all.
A concrete example of that might be helpful. So in Java, there are a truly depressing number of global mutable variables. And these are variables, some of them, on which you can't write a program that doesn't depend on these variables. I mean, you can't do I/O in Java without touching global mutables. And so the fact that some third party writes some random library that you didn't even call, right, that gets loaded into your space and runs initializers, right, your security story is now gone. And that is a language design issue. But just as an example of how stuff accreting, even if you've been careful, if the language design doesn't support the right kinds of isolations, the story goes away.
And one of the points was that global mutable statics are one of those vulnerabilities, and that you have to get rid of them to have a secure language.
That's right.
In particular, just tying it back to the definition that I gave, a global mutable static represents an ability to cause an effect on the world outside of yourself that is either, depending on how you model it, is either violates the constraint you can only cause an effect by using references that you hold, or if you model it by modeling the global environment as an object, or you model that individual variable as an object, then it violates the rule no powerful references by default, because it wasn't granted.
And I would also like to point out that indeed I don't think any of us here sitting here would refer to Java as a secure language, particularly because David Wagner here developed the Joey verifier for Java, and the Java programs that survive the Joey verifier are secure, but ones that do not are not.
I'm sorry, credit where due. David Wagner's student, Adrian Mettler.
Yes.
Yes, there's a useful distinction between secure languages and securable languages.
That's right. That's right. And that brings me to one other point that I want to clarify about what Jonathan said in his early presentation. We're now wrapping back. And I say I'm clarifying it just to suggest that perhaps I'm not actually saying that he's flat dead wrong. But one of the interesting things about the Joey verifier and about the Kaha environment for Java ECMAScript 5 and JavaScript ECMAScript 5 and about the Emily verifier for OCaml is that if you write in OCaml or Java or JavaScript, then these verifiers don't cause your code to slow down at all. You're getting the same performance characteristics. You're going to run through the benchmarks at the same speed in Emily and Kaha and Joey that you get from Java and OCaml and JavaScript. And so over at Google, where they don't in fact run everything in C++, but rather they have millions upon millions of lines of Java, if they simply ran it through the Joey verifier, they would get exactly the same performance and they would create no more heat. And if they were actually to take all of that tens of millions of lines of Java and turn it into a much smaller number of lines of Emily, they could cut their heat bills, their electricity bills in half. So object capability languages can be fast.
Yeah.
So I didn't say they weren't running Java. I didn't say they weren't running GC languages. What I said was in the large-scale server applications, there are costs of doing so that are prohibitive. And one of the unfortunate consequences of that is we end up in a bifurcated world where the really large-scale applications are going to be on legacy languages, and that's actually a problem and an opportunity space for everybody here.
I should clarify, since I'm at Google, with regard to the claims being made about how things operate at Google, this is an area of Google that I'm not in, and so I can neither confirm nor deny. I mean, I really don't know.
Whenever you're interested, I have another question.
Okay.
So a bell went off or a light bulb rang when you made the connection to concurrent programming, because then I realized that you're probably in danger of saying something you don't really mean to say and leading people in the room astray. And that is that these systems operate being secure when probably they all operate with security violations all the time, and you have mechanisms in place to confine and repair the violations. In other words, the steady state, in my talk about concurrent stuff, I'm looking at a world where the steady state is race conditions and incorrect data and repair mechanisms, and I'll bet that in the real world of secure systems, it's perfectly analogous. But maybe you meant to say, no, we can actually build things that are secure and we don't worry about the violations. Which was it?
So I think they're both. One of the most powerful effects of the object capability model as opposed to ACLs is, the way I get a file in a program is not, in ACLs is I get a file name and then I go to my authority to read anything on the disk and I look up that file name, I get that file and I read it. I have no idea whether the guy passing me the file name had the right to do that. I did, and so I got to read it. In the capability model, someone who wants me to look at the file opens the file, hands it to me, I look at that file, and I have no ability to look at any other file. The consequence of that is I can't express a program that cheats and looks at the wrong file because it has no ability to look at a file at all. It can just look at the thing the guy gave to me. And so there's a class of problems, of security vulnerabilities, that are obviated, that simply cannot be written and cannot be expressed. There's certainly plenty of, in the context of the things that can be expressed, there's certainly plenty of people trying to log in with the wrong passwords or trying to, pound on a system that doesn't want to respond to them or what have you. So that does happen all the time, but it's important to have things where you are not spending a bunch of effort to do stuff that you shouldn't have and then trying to recover because humans can't handle that.
Yeah, so I wouldn't talk about secure systems or languages for security. I would talk about insecurity mitigation, because that's what I think you're really doing. And I think it may be misleading to use the kind of language you've been using.
So there are applications where that's possible. A bank tolerates a certain amount of operating loss as a cost of doing business. There are applications where that's not possible. After the airplane falls from the sky, it's really hard to put the passengers back together. And so there's a real need to address both of these classes of problems.
Well, now, wait a minute. After the airplane gets in an unstable configuration, it's possible to run an algorithm, like if it's in a spin, adding throttle and steering into the spin to mitigate it. So you're giving me a straw man that doesn't really hold up.
It may or may not be possible. You're changing the problem. That problem, I agree, may be mitigatable, but there are certain problems that are not mitigatable. And you have to solve them both in some of these applications.
Yeah, with regard to the mitigation, I do agree that a tremendous amount, even if everybody was coding in object capability languages and everybody was coding, trying to pay reasonable attention to security, the fraction of code that has bugs in it is probably something like the fraction of code that has bugs in it now, because the economics of writing code and the economics of making code reliable is about the same. Some of those bugs are going to be bugs in security-sensitive places. However, here's the core issue. I'm saying something that I think has been said, but I want to emphasize it in a different way, which is there's two kinds of vulnerability we have from a security bug. One is whether the bug exists. I'll say whether the vulnerability exists that's created by the bug. And the other one is, how serious is the vulnerability if it does exist? What is the risk that I have from the possibility that that bug is present? And that's obviously has to be quantified over all bugs. No matter how you build a system, there'll be some modules where a bug in there just really has terrible consequences. And you try to make that as small as possible so you can afford to look at it very carefully and raise your confidence. Not to one, but raise your confidence. For a large amount of your code, one of the main benefits of the kind of security we're talking about is that we make the amount of authority available for abuse to a vulnerability, we try to make, for most locations in code, we try to make them with much less at risk. And we do that, we have to do that systematically, to emphasize Dean's point, systematically at every level, because at every level we're trying to successively reduce the authority, and there's a multiplicative benefit if you do it across levels of abstraction.
So it looks like we have another question behind you.
Oh, sorry.
Actually, before we do that, I want to add one thing, though. In the security review that we did, the Dave Wagner and I and someone else, was anyone else on that?
Yeah,
it was the four
Dean
of us.
and David attacked a system that Marc Steigler and I built.
That's right. Okay.
That was our learning experience, the first time we were seriously attacked.
Yeah. And this is our actually approximately our 10-year anniversary of that security review. And to the best of my knowledge, that was the first week-long immersive security review of a system that had been built with using modularity, extreme modularity as its security mechanism. And I would like to, while we're all here, once again thank David and Dean for totally destroying me by finding so many breaches in my code, and thereby writing the book on how not to do modularity as security.
I haven't made my point yet. Give me back that
Let's
mic.
take the question then, because we're running short of time.
Okay, so in capability security, it's very important that you take security into account throughout the entire architecture or design of your program or your system. Now, I can imagine that if you're given an object capability language or a capability secure programming language, you can probably still screw up by doing a bad design. So I wonder, what programming language features can you provide to programmers so that making a good capability secure system becomes sort of the path of least resistance?
Yes, exactly. I mean, that's exactly the right question, I think. And I think that's the kind of question that's guiding the kind of design of these languages. For instance, in an object capability language, we have this principle that code receives ability to like affect the outside world only if it's been explicitly passed that. And why do we have that principle? That principle is because that makes security the path of least resistance, because it means that code receives only stuff that's getting passed to it. And programmers, you know, the path of least resistance is to pass as a parameter the minimal stuff needed to get the job done. You have no reason to go out of your way to go pass extra stuff, right? So if you follow this kind of principle, that tends to naturally mean that code that's being called is less likely to have unneeded powers, which then means that if it has a bug, it's less likely, the severity is likely to be reduced. So exactly. I mean, I think you've nailed it.
So there was one of the things out of that security review was some features of the language that of E was the language it was implemented in that made it easier to review or harder to review, and which ones were natural. Markham mentioned that the Joule programming language was an inspiration for some of the security features in E. But one of the properties of Joule that was central to some of the design trade-offs was complete virtualization. I could have an integer, I could wrap it in a proxy and have that look completely transparently like an integer and pass it as arguments, right? And you couldn't do that in E. That was one of my, okay, this E is cool, it's a nice hack, but it's not, this beautiful, pure thing. And then we get to the security review and go, well, now I'm passing an integer. Is that really an integer, or is that a pretend integer that the first time you ask it's going to say 3 and the second time it's going to say 17? And in Joule, that would have been, sort of insurmountably part of the architecture is I'm going to pass you this thing that might be a different, might induce a time of check, time of use bug. And one of the features of E to be able to force grounding of that made it easier to say okay, here's a security boundary, let's nail it down. Is that an integer or not? Right? And it was very straightforward to then realize that they had to add this thing. And in fact, they had a bug where it might have been, it might not have been, but it was easy to lock it down.
So this is a comforting story, but it's completely wrong. Okay? This is true in the same way that saying that a program that puts up a dialog box that says, is it okay to penetrate your system now, and you have to hit OK, that because you have to hit OK, something got better. Well, we all know that the damn thing comes up and says, is it okay? And we say, yeah, sure, it's okay, get out of my way, right? However, and I used to find this story comforting, and then I thought about it. I actually think there's a different reason why the need to pass things explicitly turns out to help in a statistical sort of sense, or in a weak sort of sense. And it's not because the guy passing the parameters cares, he's just trying to get a job done. Okay? And if you've ever seen anybody doing agile programming, you know that the goal is to minimize the level of thought involved in using the next guy's code, and ideally to reduce it to 0. However, if you're the guy writing the code, every parameter you add to your procedure is a pain in the butt. Okay? So you try not to ask for things that you shouldn't want. I actually think that's probably a more likely story about the source of improvement in this scenario. I'm sorry, Dave. But,
well, and similarly, and that actually works with the thing that I described, because the guy who's writing the procedure is the one that's sort of implicitly creating a security boundary. If he says, I want an int, just give me a damn int, and then you don't have to think about it, and it's this ground type that everyone, that he deeply understands and isn't going to be surprised by, that turns out to be a win, for the lazy programmer. Right?
For the language designers here who are tempted to design an object capability language of their own, I also have another story from E, from the early days of E. In functional languages, of course, the very last evaluation inside the framework of the function is implicitly returned as the value of the result of the evaluation. Okay, and the very first version of E had this characteristic that whatever random thing happened to be the last evaluation at the end of a method was the thing that was being returned. And that was very nice and convenient when the method was supposed to be returning something. But I kept on telling Mark Miller for over a year that if you had a method that you were expecting to return nothing, and it actually returned something, then you were leaking authority by default.
Yeah. And for most of that year, I firmly believed that first of all, that expression languages were great, lambda calculus was great, and that really object capability programmers wouldn't make that mistake. And certainly I believed I wasn't making that mistake.
And of course, what happened, the reason why there is now an explicit return at the end of a method in E is that one day we discovered that a piece of code that Mark Miller had written was accidentally, implicitly returning a very powerful file authority at the end when it was supposed to be returning a null.
So yes, design of the language matters.
Yes.
Thank you.
So I've got a question and a comment, actually. So I start with a little comment.
A little louder, please.
So I've got a little comment at the beginning that is just like, so when you say object capabilities are important, I kind of agree with that, but so why are we still using languages where area access can lead into index out of bounds, right? So that is, for me, like a capability, right? You shouldn't be able to access an area out of the bounds. I don't know if you have something to say for that. But my real question is, so given that object capabilities are important, they are one means to restrict access to stuff that you don't want to leak, right? But research has also had this notion of end-to-end security, which means that sometimes you have to give access to stuff because some part of the code needs to know a secret, because like your credit card number needs to go to pay for your purchase. But then, once the code has been given access to that secret, can you make sure that the credit card number is not used for something else? Once you give it out, it's gone, right? Is there anything you can do with object capabilities for that?
Okay, so depending on your circumstance, there's one particular pattern that predates my involvement with object capabilities that helps you in some of these, and it's called the sealer-unsealer pattern, wherein if you can give the guy who's supposed to be using something the unsealer, and you've got the sealer, then you can pass the sealed box through all of these things that you do not trust. And eventually it will get to him at the far end. And then you can make it a use once authority like the one that I showed in my demo, and sometimes that will help you with the kinds of problems that you just described.
Go ahead.
Yeah, I was just going to say, sure, you can make sure that the stuff that you don't trust doesn't get it, but the stuff that you must trust must get access to that. And who says that this is not a Trojan horse?
Yes, so I'll make a slightly different claim, which is if you ever give a secret to some code you don't trust, you lose. There is no other, I think, sound stance you can take, because if malicious code gains access to a secret, there are a gazillion ways it can leak it out. I want you to imagine a prisoner in a prison cell who's been told a secret. You cannot prevent that prisoner from communicating with other prisoners by banging on the walls. And in the programming language world, there's 101 ways to bang on the walls, including, for instance, modulating the load of the system to affect the response time it has to pings sent by someone on the other side of the world. So these kind of covert channels, storage channels, timing channels are essentially impossible. It's essentially impossible to close them off and prevent someone from sending on a storage channel. It is possible to prevent untrusted code from listening on a storage channel, but you cannot prevent it from sending on a storage channel. And so the consequence of that is, if you have a secret, don't give it to anyone you don't trust.
You mentioned the problem of a capability that comes to you over a series of steps, and by the time it gets to you, you don't know if it's authentic. It's not quite what you said, but
Say it again,
You were expecting some capability to come through a channel, and it comes through a series of hops with various parties in the middle. And by the time it gets to you, you don't know if that's the capability you were expecting or some front-end application that simulates it, for example. It could be something else entirely. There actually is a design pattern that deals with that. It's called the brand mechanism. And I don't want to take the time to walk through how it works here, but there is at least a fairly strong solution to that.
Yeah, it's actually similar to the sealer on sealer that Marc Steigler was talking about.
But the other thing I want to throw out, just for people doing PL stuff, just a quick poll of the room. How many of you know what a capability is or what a capability system is?
Good
okay,
grief.
That's really surprising. That's a higher percentage than I think I've ever seen before.
Yeah, I want to applaud the audience for that.
Yeah,
Yes.
absolutely.
I've seen that before.
Apparently, the collective 100 years we've put into this made some headway. There's an interesting opportunity now. Until very recently, until capability systems were kind of intellectually taking hold, it was very hard to reason across the operating system language boundary. Right? So you would see people do security analyses of access control policies, which went, okay, we're going to start with a certain configuration of the machine. We're going to assume that all programs are as evil as they can possibly be. And then we're going to ask if the policy gets violated, given this initial configuration of the machine. Now, this analysis is kind of crazy, right? I mean, it's valid in the sense that if you don't trust the program, indeed, you should assume that it's maximally hostile, because that's kind of the conservative assumption in this analysis. What it doesn't let you do is reason in any way at all about the impact of trusted programs in a system. And historically, the way we've had to do this is we embed the behavior of the trusted program in the model that we're reasoning about. Okay? And part of the reason that we had to do that is we couldn't connect what happened when you had an OS level message to what the program did semantically. So nowadays, I think we have a handle on software verification for at least certain very small classes of programs. And programs that enforce security properties are either that small or you need to get rid of them and make them that small, because you don't have any hope of getting them right if they're much bigger. And because at the operating system level, we're now talking in terms of capabilities, which are basically object references. Right? And capability, in some sense, can be viewed as designating a closure in the receiving program. And we know how to reason about what happens there, formally. Right? So it's now possible to extend our system security models to talk about the behavior of trusted programs. And that's actually a really interesting new opportunity for those of you who are doing PL-oriented security research, right? There's now an opportunity to build sort of an end-to-end picture across that previously very dismally opaque layer. And that's a huge opportunity for people who want to do policy stuff.
So I wanted to add one more follow-up, which is actually on David's thing, but that was a good point you made. Okay. In the case of I disclosed a credit card number to some program, I've disclosed it, and if it can wall bang, and it can, then it can disclose that secret. It is important, or it is useful, to distinguish between data and other capabilities. Because I can disclose a credit card number, which is sort of like a capability to my money, except that it's represented as data, which can be wall banged. If I give you an object pointer, wall bang the address all you want. That's not going to do the other guy any good. He cannot forge a pointer to the object that I gave you. And so that it is much more straightforward, much more feasible to confine. So I can take a program, launch it in a sandbox that I handed an object to. It can party on the object, and it can't give it to anybody else. Now, it can still proxy it by doing wall banging. Basically, wall banging is just a low bandwidth channel. So it can, layer another communications thing on it and proxy access to the object I gave it. But at least I can give it the object, run it for a little while, and then throw that program away. And now it's done. Now my exposure is closed, and it can't have leaked any ongoing access to that thing I handed it. So there are, in fact, patterns that give more restrictions than merely if you've disclosed it to that program, you're out of luck.
This, by the way, suggests another great research paper. Write and benchmark a covert channel SDK.
You asked, why isn't everyone using capabilities? I don't know if I'll get the last word, but I'll throw in a controversial claim. I think maybe it's for pretty much the same reason that not everyone in the world is using functional programming. It's a great idea, but there's a lot of historical inertia. That's debatable. That's absolutely debatable. I'll leave you with a debate question.
Oh, no. The big difference is functional programming is a great idea that people have a hard time understanding. Capability security stuff, given the success of object programming, people are really good at understanding that, and we've learned a lot from them and brought it over to security, and now it's just a question of realizing that they can use that same set of tools to do security stuff.
There's actually a deeper connection here that I only became aware of when I was talking to Eric Meyer, where I was talking object capability, he was talking functional programming, which is to the degree that functional programming is a good idea, which we can debate, but let's grant that there is some substantial argument for it. What is the argument? The argument is it's difficult to think about effects. So uncontrolled effects of imperative programming, as we're used to, is difficult to think about. Functional programming is going all the way to the other extreme. Let's get rid of all effects because they're so hard to think about. But object capability programming, one way to think about it is it's a midpoint between conventional imperative programming and functional programming. It still allows imperative effects, but it provides you tremendous tools for reasoning about limitations on who can affect what. And that kind of disciplined reasoning about effects is a very interesting intermediate point.
So what you're saying is it's not really a choice between functional and dysfunctional?
Thank you all.
Thank you.
Thanks.
Thank you.